On the factory floor, the rhythm is its own language. The staccato of rivet guns, the low moan of presses, the steady clank of conveyor rollers. A wing rib moves on a jig, then another, then a half dozen, identical, interchangeable, marching toward the point where sheet metal becomes machine. An engine is bolted into a nacelle. A bubble canopy is lowered into place. Aluminum skin glints under shop lights. A Mustang, in pieces at dawn, is a Mustang in flight by dusk. Hours later, that same metal and oil and human muscle will find itself singing over Mount Fuji. What the camera sees in a single frame of sky, sleek fuselage, a pilot's silhouette behind a clear dome, tracers cutting through cloud, was for weeks, months, sometimes years, the work of men and women on an assembly line. Inside the factory that built the P-51 Mustang that shocked Japanese pilots over Tokyo, strategy took on rivets and tolerances, and a geopolitical contest boiled down to throughput, standardization, and repeatable quality. They called it production as a weapon. At peak periods, the line was turning out roughly one Mustang an hour. By war's end, American industry had produced 15,586 Mustangs in all. The D model, the version pilots came to trust over Tokyo and the open ocean, accounted for 8,156 of them. Those figures are not mere statistics. They are a measure of scale. The number of fuselages joined, engines run on test stands, and pilots trained to climb into cockpits that rolled off the line like an argument settled by repetition rather than by gamble. The heart of that argument was not only the airframe, but the heart under the cowling, the Packard-built Merlin. Rolls-Royce's Merlin engine, licensed to Packard in Detroit, reunited advanced British supercharger design with American mass production. A licensed engine line in the United States meant that the aerodynamic advances of North American aviation could be paired with the horsepower needed at altitude. In production terms, that pairing was everything, an economic equation that translated into endurance, speed, and presence over distant target sets. Factories do not merely assemble, they standardize. Interchangeable parts reduced repair times in the field. Subassemblies could be swapped in forward depots. Wings, control surfaces, instrument panels, each component traced back to a drawing and a tolerance. Quality control stations checked critical assemblies at every step. Aircraft that had to be repaired at island strip lines or field depots would arrive in modules, and the ability to swap a damaged piece for a serviceable one without bespoke fitting cut downtime dramatically. That was the logic behind a Mustang leaving the plant whole. Every bolt, every hose, every panel was specified so that maintenance crews could repair them fast, keep them flying, and keep squadrons at strength. Think of the assembly line as a clock. If one station slowed, the whole rhythm altered.
Management, material supply, machine maintenance, and trained labor all had to be synchronized. Liberty ships carried the raw material, trainways moved parts inland, and aircraft carriers and forward bases returned the damaged machines to repair loops. The factory was the origin point of a system, not only planes, but spare engines, standardized tools, and manuals that allowed the airplane to be more than a machine, an operable system in combat. If this sounds like industrial engineering writ large, that is because it is. The Mustang's presence over Tokyo was an operational fact only because of supply chains that crossed oceans, because of licensing agreements that moved a British idea into American manufacturing, and because of management decisions that prioritized reliability and maintainability as fiercely as top speed. If you want a deep technical breakdown of the Packard Merlin and archival assembly line footage, subscribe and hit the bell. There's a detailed segment on engine production and test runs coming up in this series. The airplane itself was an exercise in deliberate trade-offs. Designers sought a clean aerodynamic shape, a high-performance engine, and enough fuel and armament to make escort and interception credible across long distances. The laminar flow wing is one of those design choices often misunderstood outside aeronautical circles. In plain terms, laminar flow is about smoothing. It is like clearing a traffic bottleneck so air can glide over the wing with less friction. Less friction at cruise speeds means less drag, and when combined with an engine that breathes well at altitude, results in higher speed and longer range. For pilots crossing hundreds of miles of empty ocean, that improvement in drag was not academic. It was the difference between making contact with long-range bombers and turning back. The Packard Merlin's role at altitude requires a one-line explanation. It used a two-stage, two-speed supercharger with an intercooler. That phrase can be broken down into a simple idea. A supercharger compresses incoming air so the engine breathes more oxygen at high altitude, where the air is thin. Two-stage, two-speed means the compressor has two levels of compression and can operate at two different gearings, optimized for different altitude bands. So the engine can make more power across a wide vertical range. An intercooler cools compressed air before it reaches the engine, preventing power-robbing knock and allowing higher boost settings safely. Put together, these features let the Mustang hold power and speed high above the deck, where escorting heavy B-29s and intercepting enemy fighters mattered most. Pilots and mechanics felt those design choices in the cockpit and on the maintenance logs. The bubble canopy, another D-model innovation, offered a nearly unobstructed 360-degree field of view compared with earlier framed canopies.
In a dogfight, the difference between a framed view and a bubble could mean spotting an attacker before being surprised. Drop tanks, external jettisonable fuel tanks, extended the reach of a single-engine fighter across the Pacific. Loaded on the wings or centerline for outward legs, they increased range at the cost of some drag. Once over the target area, pilots could jettison them and regain a cleaner, more maneuverable aircraft. The trade-off was calculated and repeatable, part of an operational doctrine that trusted logistical planning and standardized loadouts over improvisation. Armament on the P-51D was straightforward and reliable: 6.50 caliber M2 Browning machine guns. These weapons were robust, abundant in American logistics, and effective against both aircraft and lightly armored ground targets. The combination of stable, predictable firepower and the Mustang's speed and altitude performance made it an ideal escort and interceptor. It was not invulnerable. No single-engine fighter could be. But designers and logisticians emphasized durability and maintainability as much as peak performance figures. Those numbers, production totals, operational rates, are not abstract. At Ibrahima, one forward maintenance and operational point identified in reports, P-51 units routinely posted serviceability figures above 80%. That meant the majority of the Mustangs assigned to a squadron were mission-capable at any given time, a staggering logistical advantage when contrasted with the condition of many Japanese fighters late in the war. Reports indicate Ki-84 units on numerous airfields were often hampered by serviceability rates that frequently fell below 40%. The Ki-84's theoretical performance was impressive on paper, a potent airframe with promising speed and climb. In practice, shortages of high-quality materials, fuel, and spare parts, coupled with fractured training pipelines and overstressed maintenance crews, turned theoretical advantage into operational weakness. The airframe alone does not win battles. The ability to keep machines flying and armed day after day does. Maintenance rates are where industrial capacity and combat effectiveness converge. A plane that sits idle is a plane that cannot alter the ground truth. Rapid replacement of parts from standardized bins, the ability to cannibalize non-critical aircraft for critical spares, and a logistics tail that could deliver engines, hydraulics, and new propellers on ships and transports. These were the invisible muscles behind the Mustang's presence in the skies. The factory fed these muscles with repeatable output, and the system of depots and repair shops kept that output in the air. There is a human scale to that industrial network. Ground crews learned to recognize the unique signals of the Merlin, its idling note, its breathing, and their practices evolved to match. Pilots, in turn, learned the serviceability profile of their machines. Which instruments were most fickle? Which hoses tended to head for leaks after extended missions? And how to manage fuel to preserve engine health? Training hours mattered. Not every pilot reached the same proficiency. And in the latter stages of the war, Japanese pilot training suffered severe degradation. The American system, with its standardized procedures and abundant spares, allowed a fresher pilot to step into a cockpit and count on the airplane to behave predictably. That predictability, multiplied by thousands of missions and facilitated by the factory's output, reshaped what air operations could attempt. Scale also meant mathematics of supply. To keep a squadron flying on long-range escorts required more than planes. It required pipelines of fuel, boxes of ammunition, spare propellers, and replacement Merlins ready for exchange. Liberty ships crossing the Pacific carried aviation gasoline and components in standardized packaging. Aircraft transport planes like the C-54s shifted high-priority parts quickly between logistics hubs. On the islands, forward depots kept a rolling inventory calibrated to expected wear rates and known failure modes. Those numbers, how many gallons of fuel per sortie, how many rounds expended in an average engagement, how many hours elapsed between major engine overhauls, were inputs to planning. They were the terms of a constraint optimization problem. Get enough force over the target without draining the supply tail beyond repair. American industrial output dwarfed Japanese production by late-war metrics. The Mustang line, cranking out thousands of airframes, was one part of a broader ecosystem of American manufacturing that could absorb losses, replace machines, and scale up operations. On the Japanese side, production increasingly encountered bottlenecks. Fuel shortages, material scarcities, and disruptions from bombing campaigns that reduced factory capacity. Quality control degraded too, as skilled labor was stretched thin and materials were substituted or rationed. This is not to deny technical skill or courage. Key 84 crews and their units continued to fight with resourcefulness. But scale and logistics began to dictate the terms of engagement. How many aircraft could be maintained in the air for the sorties needed to contest the skies over home islands? So when a squadron of Mustangs prepared for a very long-range escort across hundreds of miles of open ocean, it was not merely a test of pilot skill, but a live demonstration of that system. The April 7, 1945 mission to Tokyo, one of the instances when single-engine fighters materialized over the Japanese capital, was the sort of operation that required alignment across factories, engines, logistics hubs, and crews. Briefings the night before were precise and quiet. Pilots reviewed navigation waypoints that involved long stretches with no visual references, fuel tables calibrated to winds aloft, and emergency procedures for ditching in a vast sea if engines failed. Aircraft were checked to tolerances learned on the line, hydraulic systems pressured, control surfaces checked for play, fuel lines inspected. Drop tanks were filled and secured. Armament was verified. Ground crews performed final runs of engine checks and verified that the Packard Merlins were running within expected parameters. Pilots wrote final notes in logbooks, adjusted oxygen fittings, and climbed into cockpits where instruments reflected the careful work of the factory and the maintenance shops. Takeoff across a forward strip was a study in choreography. Dozens of Mustangs, each an identical answer to an engineering problem, threaded between revving engines and dust plumes. Formation flying for VLR missions was not showmanship. It was fuel economy and mutual support. Mustangs would form up with B-29 formations at prearranged rendezvous points. The fighter pilots trained to the narrow window of timing that allowed interception or escort without undue fuel waste. Navigation took a different kind of rigor out on the ocean. No friendly landmarks for much of the sortie. Only the sun, barometric readings, dead reckoning, and radio fixes. The laminar flow wing and Merlin pair acted quietly in the background, delivering the expected cruise speeds with sufficient fuel efficiency to make the rendezvous point plausible. Drop tanks extended the flight time, but they did impose constraints. Pilots would monitor fuel burns constantly. Conservative fuel management was the rule, because over the Pacific one could not rely on luck. For crews on the other end of those missions, the Japanese defenders, seeing Mustangs over Tokyo was not merely a tactical problem. It was a psychological rupture. In airfields and control rooms, reports began to describe disbelief. Single-engine fighters not only arriving over the capital, but flying at altitudes and with endurance that seemed beyond expectation. Flight Sergeant Totanimizu of the 56th Senti, in later recollection, described the sight as uncanny. Machines he had been trained to engage did not conform to previous encounters. Captain Yoshio Yoshida of the 47th Senti recorded similar surprise in operational notes, noting that Japanese preparations had been tuned to intercept threats of different profiles. These were professionals confronting a new operational reality, one partly created in distant factories and supply depots. On the American side, pilots noted the effect their presence had on ground observers. Major James B. Tapp, who flew escort missions, later reflected on how the sight of Mustangs over the heartland of Japan changed the atmosphere. Not merely military posture, but the psychological weather.
Captain Art Bridge of the 45th Fighter Squadron recalled the moment of first sighting with a mixture of clinical detail and the slow astonishment of an eyewitness. The Japanese reaction, rushing to scramble, mistaken assumptions about numbers and capability, was part of the mission's impact. The April 7 approach turned tense as navigation led the formations over the final stretch toward Honshu. Crews scanned the horizon. Overhead, the profile of the coastline unfolded. Radio operators pinged for positions. The formation tightened because in a contested environment, proximity was security, mutual support against the unexpected. Trained to keep the B-29 safe from fighters and flak, Mustang squadrons assumed roles that put them between bomber and enemy, triangulating potential threats and using their altitude and speed to deny attackers the initiative. Then came the sighting. Enemy fighters in the vicinity of Tokyo, alert and ready. The shock registered both on the American side and among Japanese pilots. The image of single-engine Mustangs over the capital had been, for many on the receiving end, improbable. Lieutenant Jerry Yellen of the 78th Fighter Squadron would later note how the Japanese formations maneuvered with a blend of skill and desperation. Skilled because many pilots retained instinctive air combat ability. Desperate because resources, fuel quality, and experience were running thin. On the ground, scramble controllers fed pilots into the sky with a sense that this was no ordinary interception. A confrontation of sorts began to form. The Mustangs, designed to operate at altitude and with the endurance to stay with long-range bombers, held advantages in predictable climb and power. The Packard Merlin supercharger allowed pilots to hold speed and compression where the thin air would normally rob engines of power. For Japanese pilots, the Ki-84 and other types could be formidable, but late-war realities, deteriorating maintenance standards, erratic fuel quality, and supply shortages meant these advantages often fell short of their promise in sustained engagements. As the two sides closed, the feel of tension sharpened. Pilots switched to combat radios, fingers on triggers, eyes scanning for closure. The technical features that began in factories, laminar wings, dependable Merlins, rugged armament, and methodical maintenance, now translated into tactical options. Altitude advantage, reliable climb rates, and sustained firepower within expected envelopes. At the same time, the human dimension, fatigue, experience, morale, loomed large. Many Japanese pilots were young, less trained, and operating machines whose serviceability was uncertain. Many American pilots, too, were stretched by continuous operations and long flights.
The first visual contact over Tokyo was not instantaneous fireworks. It was a cascade of processes, pilots reporting sighting bearings, flight leads assigning sectors, and individual machines beginning to close.
Tracers would soon lace the sky. The sound of engines would stamp the air. But at the moment before collision, there is a distinct, almost clinical pause in which the industrial story and the human story meet, the product of factory lines aligning with the skill and nerves of individual airmen. It was here, in the minutes before the first shots, that the factory's contribution could be measured not in steel, but in the tactical choices it enabled. And then the first reports came through the radio. Flashes of engagement, short, precise, and urgent. Flight leaders called for support, pilots reported hits and misses, and the long numerical chain that began in steel mills and machine shops revealed itself in the bursts of action over Tokyo. The fight that followed would test not only design features, but also supply lines, repair loops, and whether maintenance depots could replace what battle chewed up. But before the smoke and the tally of losses and returns could be fully known, the April 7 mission entered a dangerous, weather-dependent phase. Clouds scudded in from the ocean, and visibility fluctuated. Black Friday light conditions had proven fatal in other operations. Weather could erase the advantage of power and production, turning predictable patterns into peril. Pilots had to balance aggression with caution. The Pacific offered few safe havens for those who misjudged fuel or cloud. As the formations peeled away and engagements concentrated over the capital, the factory remained a quiet participant in the drama. The Packard plants continued to turn out Merlins. The assembly lines in the heartland continued to splice metal into wings. Logistics trains continued to shuffle spares. Each damaged or lost Mustang was a call into that supply chain. Spare parts requisitions, engine replacements, and the reshaping of sortie schedules. The frontline combat would determine immediate outcomes. The factory determined whether the fight could be sustained again and again across weeks and months. At the edge of the engagement, a Mustang pilot radioed a terse report of being low on fuel after a skirmish, an all-too-common note on VLR missions. Crews had to time the jettison of drop tanks to conserve weight and drag, picking the moment when offensive maneuverability outweighed the endurance the tanks provided. Every decision was a microcosm of factory-era logic. Optimize for the mission profile, but accept that the material limits set by fuel and wear are immutable. Reports from Japanese fields described hurried attempts to patch aircraft between sorties, cannibalizing serviceable components to get a single plane airborne. The language of scarcity, stripped rivets, scrounged parts, repeated across maintenance notes. This was not absence of skill, it was the arithmetic of depletion. Where American depots could send replacement Merlins and new propellers, Japanese units increasingly faced a slower, more improvisational process of repair. In the sky above Tokyo, that arithmetic began to show in the exchange rates of sorties to sustained capability. The May and June operations had already exposed the limits of both sides. The April 7 mission would add one more data point. As the dogfights continued and the escorting Mustangs swung between protecting bombers and engaging interceptors, the underlying narrative grew clearer. The factory's work, translated into numbers of aircraft and rates of serviceability, allowed the United States to attempt operations that earlier seemed unlikely. The presence of a single-engine fighter over a capital city, an image that once would have been dismissed as impossible, now became a repeatable tactic because production and logistics could support it. Yet, even as momentum gathered, vulnerabilities remained. Weather could still disrupt anything. Operational losses accumulated. Pilots and crews faced exhaustion. For every Mustang that returned, another might be irreparably damaged or lost at sea.
The factory's output could replace many losses, but not erase the human cost that accompanied every mission. The April 7 mission's narrative, therefore, is not a simple tale of technological triumph. It is a layered account. Factories shaping possibilities, engineers refining performance envelopes, logistics ensuring that those envelopes could be exploited, and pilots translating all of this into action under the most unforgiving conditions. Each plane that climbed off a production line embodied a chain stretching from drawing board to forward strip, and every mission was an experiment in whether that chain could hold. Moments after the first violent exchanges, radio silence and static mixed with urgent calls for returns and emergency landings. A Mustang that had been rolling off a line in a Midwestern factory weeks earlier now found itself trailing smoke and low on fuel over the Pacific. Ground controllers began calculating recovery options. Repair depots started inventory checks for a possible engine transplant. The industrial clock started to tick. How quickly could a replacement engine be shipped, installed, and tested? The answer would determine whether the squadron's tempo would be restored. On the Japanese side, pilots who managed to land on damaged strips were often met by crews doing what they could with less. Lieutenant Colonel John R. Morgan, who flew reconnaissance and knew the limits of forward maintenance, later recorded in dispatches how the combination of attrition and supply shortfalls affected sortie generation rates. The contrast between balanced industrial input and fraying logistical support on the Japanese side rendered engagements increasingly asymmetrical, even where technical parity in airframes might have existed on paper. The sky over Tokyo on that day was, in a sense, the factory's shadow.
It was a place where the abstract calculus of production, throughput rates, spare part inventories, and test stand metrics met the messy reality of combat: smoke, human error, weather, and courage. The next hours would decide which elements of the system held and which frayed. And beneath the immediate drama, teams back home and at forward depots were already responding to casualty reports, reprioritizing shipments, and prepping engines for testing. The factory did not sleep. Its work shifted from producing new machines to replenishing the material base needed to keep existing ones aloft. As the mission proceeded deeper into the urban airspace, the aviation historian's ledger would register the raw counts: planes claimed, pilots lost, and aircraft that made it home damaged but flyable. Yet those tallies are only one layer. More consequential, for strategy and for the men who watched the skyline change that day, was the realization that single-engine fighters operating from distant islands could, in fact, appear over the capital with deliberate frequency. The factories had proved they could not only build speed and altitude into an airframe, but also turn that capability into sustained presence. The engagement over Tokyo began to resolve into a series of smaller encounters, pairs and trios of fighters, brief slashing attacks, desperate defensive spirals. Pilots faced a calculus they had rehearsed on the ground: conserve fuel, protect the bombers, engage when the odds favored you, and above all, bring the airplane back. For both sides, the material and logistics scaffolding framed those choices. When a Mustang's Merlin coughed and died, it brought into focus the entire supply chain that could replace that engine. When a Ki-84 struggled to respond after repair, it reflected shortages that could not be fixed at the unit level. The day's fighting would leave records, reports, and later recollections. Lieutenant Philip Schlomberg's last combat mission, Lieutenant Jerry Yellen's after-action reports, and the dispatches of Brigadier General Ernest M. Moore of the 7th Fighter Command would enter official files and, eventually, the historical narrative. Captain Harry Krim Jr. and other squadron leaders would tally sorties and losses, and their notes would feed the loops back to depots and factories, deciding what to prioritize next. But the immediate urgency of the sky, planes in combat, radios clipped and terse, pilots balancing missions and fuel, would soon give way to another kind of reporting. Recovery crews on the islands would start the slower work of diagnosis. Mechanics would catalog battle damage, estimate hours to repair, and send requisitions to forward depots. Engineers at the origin factories would cross-reference damage types with parts inventory, looking not only at production quotas but at the changing spectrum of attrition. The day's fighting would leave records, reports, and later recollections. Lieutenant Philip Schlomberg's last combat mission, Lieutenant Jerry Yellen's after-action reports, and the dispatches of Brigadier General Ernest M. Moore of the 7th Fighter Command would enter official files and, eventually, the historical narrative. Captain Harry Krim Jr. and other squadron leaders would tally sorties and losses, and their notes would feed the loops back to depots and factories, deciding what to prioritize next. But the immediate urgency of the sky, planes in combat, radios clipped and terse, pilots balancing missions and fuel, would soon give way to another kind of reporting. Recovery crews on the islands would start the slower work of diagnosis. Mechanics would catalog battle damage, estimate hours to repair, and send requisitions to forward depots. Engineers at the origin factories would cross-reference damage types with parts inventory, looking not only at production quotas, but at the changing spectrum of attrition.
The operational picture and the industrial picture were contiguous. Each sortie informed production priorities, and each production decision altered the nature of future sorties. The April 7 mission was a revealing instance of that interaction. It showed how a product of industrial repetition, a Mustang rolling off a line, could be allied with strategy to produce effects that, a few years earlier, were assumed impossible. Yet, at every step, that effect was contingent on weather, on pilot skill, on the ability of maintenance crews to keep machines flying, and on supply chains that synchronized across an ocean. Now, as the engagement intensified and the first returns began to stream back to base, forward commanders and depot chiefs were already at work parsing what had been consumed and what would have to be replenished. The factory's output, steady as it could be, was one factor among many, but it was a crucial one, a continuous source that could turn tactical experiments into sustained doctrine. The question the hour posed was whether that chain, from drawing board to assembly line to maintenance bench to sky, would continue to hold under mounting strain. The answer would depend on many things, including whether weather improved, whether replacement parts could be rerouted fast enough, and whether pilots on both sides could endure the attrition and stress of repeated long missions. The drama over Tokyo punctured assumptions and crystallized a new operational reality. But the aftermath, repairs, replacements, the sobering readouts of losses, would determine how soon such missions could be repeated and at what cost. At the thin edge where industry meets combat, decisions were being made that would shape the coming days. Which component shortages to prioritize, which production lines to speed up, and which repair protocols to simplify. The factory that built the Mustang had done its job in producing machines. Now the wider system, logistics, maintenance, and human endurance, was being tested to see whether those machines could continue to be a presence over Tokyo instead of a one-off demonstration. Outside the immediate flurry of engagement and return, cultural and psychological effects began to ripple. Observers in Tokyo, both military and civilian, registered the incursion not only as a military event, but as a sign of changing fortunes. In the recording rooms of intelligence officers and in the reports of squadron commanders, the question shifted from "how did they get here?" to "how often can they come?" That was the moment the factory's role converted from an industrial fact to a strategic variable.
If production held and logistics sustained, what once seemed tactical novelty approached the status of operational doctrine. But these strategic reverberations would take weeks and months to resolve.
For now, on the immediate runway and in the smoke-streaked skies above Tokyo, the focus remained unforgivingly particular, bringing damaged machines back, counting the living and the dead, and filing requisitions for the next rotation of flights. The factory's quiet hum, far from the front, would continue to be the necessary precondition for those next flights. And the people who kept those lines moving, engineers, machinists, inspectors, occupied a different kind of front line, one that operated in the long-term calculus of sustainment rather than the moment-by-moment survival of aerial combat. As sun slid westward, the day's sorties tapered and reports began to coalesce. Commanders paged through patchy radio logs, maintenance officers tallied damage types, and depots began to prioritize shipments. The April 7 mission would appear in after-action dossiers as a complex episode. Tactical successes tempered by losses, operational insights shaded by weather and attrition. If the Mustangs had indeed shocked Japanese pilots, that shock was both technological and psychological, byproduct of design choices and, crucially, the scale at which those choices were produced and maintained. The rest of the story would unfold over the following days and weeks, how maintenance cycles coped, what replacements arrived from factories, and whether the operational tempo could be sustained. But in the last light over the Pacific, on the factory floor, the rhythm is its own language. The staccato of rivet guns, the low moan of presses, the steady clank of conveyor rollers. A wing rib moves on a jig, then another, then a half dozen, identical, interchangeable, marching toward the point where sheet metal becomes machine. An engine is bolted into a nacelle. A bubble canopy is lowered into place. Aluminum skin glints under shop lights. A Mustang in pieces at dawn is a Mustang in flight by dusk. Hours later, that same metal and oil and human muscle will find itself singing over Mount Fuji. What the camera sees in a single frame of sky, sleek fuselage, a pilot's silhouette behind a clear dome, tracers cutting through cloud, was for weeks, months, sometimes years, the work of men and women on an assembly line. Inside the factory that built the P-51 Mustang that shocked Japanese pilots over Tokyo, strategy took on rivets and tolerances, and a geopolitical contest boiled down to throughput, standardization, and repeatable quality. They called it production as a weapon. At peak periods, the line was turning out roughly one Mustang an hour. By war's end, American industry had produced 15,586 Mustangs in all. The D model, the version pilots came to trust over Tokyo and the open ocean, accounted for 8,156 of them. Those figures are not mere statistics. They are a measure of scale. The number of fuselages joined, engines run on test stands, and pilots trained to climb into cockpits that rolled off the line like an argument settled by repetition rather than by gamble. The heart of that argument was not only the airframe, but the heart under the cowling, the Packard-built Merlin. Rolls-Royce's Merlin engine, licensed to Packard in Detroit, reunited advanced British supercharger design with American mass production. A licensed engine line in the United States meant that the aerodynamic advances of North American aviation could be paired with the horsepower needed at altitude. In production terms, that pairing was everything, an economic equation that translated into endurance, speed, and presence over distant target sets. Factories do not merely assemble, they standardize. Interchangeable parts reduced repair times in the field. Subassemblies could be swapped in forward depots, wings, control surfaces, instrument panels, each component traced back to a drawing and a tolerance. Quality control stations checked critical assemblies at every step. Aircraft that had to be repaired at island strip lines or field depots would arrive in modules, and the ability to swap a damaged piece for a serviceable one without bespoke fitting cut downtime dramatically. That was the logic behind a Mustang leaving the plant whole. Every bolt, Every hose, every panel was specified so that maintenance crews could repair them fast, keep them flying, and keep squadrons at strength. Think of the assembly line as a clock. If one station slowed, the whole rhythm altered. Management, material supply, machine maintenance, and trained labor all had to be synchronized. Liberty ships carried the raw material, trainways moved parts inland, and aircraft carriers and forward bases returned the damaged machines to repair loops. The factory was the origin point of a system. Not only planes, but spare engines, standardized tools, and manuals that allowed the airplane to be more than a machine, an operable system in combat. If this sounds like industrial engineering writ large, that is because it is. The Mustang's presence over Tokyo was an operational fact only because of supply chains that crossed oceans, because of licensing agreements that moved a British idea into American manufacturing, and because of management decisions that prioritized reliability and maintainability as fiercely as top speed. If you want a deep technical breakdown of the Packard Merlin and archival assembly line footage, subscribe and hit the bell. There's a detailed segment on engine production and test runs coming up in this series. The airplane itself was an exercise in deliberate trade-offs. Designers sought a clean aerodynamic shape, a high-performance engine, and enough fuel and armament to make escort and interception credible across long distances. The laminar flow wing is one of those design choices often misunderstood outside aeronautical circles. In plain terms, laminar flow is about smoothing. It is like clearing a traffic bottleneck so air can glide over the wing with less friction.
Less friction at cruise speeds means less drag, and when combined with an engine that breathes well at altitude, results in higher speed and longer range. For pilots crossing hundreds of miles of empty ocean, that improvement in drag was not academic. It was the difference between making contact with long-range bombers and turning back. The Packard Merlin's role at altitude requires a one-line explanation. It used a two-stage, two-speed supercharger with an intercooler. That phrase can be broken down into a simple idea. A supercharger compresses incoming air so the engine breathes more oxygen at high altitude, where the air is thin. Two-stage, two-speed means the compressor has two levels of compression and can operate at two different gearings, optimized for different altitude bands. So the engine can make more power across a wide vertical range. An intercooler cools compressed air before it reaches the engine, preventing power-robbing knock and allowing higher boost settings. Allowing higher boost settings safely and preserving breath through the thin air where fights for altitude were decided. That combination, an aerodynamically clean airframe married to a supercharged mass-produced engine, was the core mechanical promise the factory delivered. But engineering promise only becomes military effect when the plant's rhythms, the supply chain's cadence, and the human practices of maintenance and flying all line up. The rest of the story is about how those pieces fit together, how seams were sealed in the American system, and how the seams in the Japanese system began to open under strain. On the line in Detroit and other plants, Packard's Merlin assembly showed the same instinct for repeatability that marked the airframe factories. Jigs that held crankcases at precise tolerances, test stands that ran engines through prescribed cycles, and quality gates that would not let a unit proceed until instrument readings matched spec. Engines left the line with nameplates and test records. When they reached forward depots, mechanics could read the logs and set expectations for overhaul intervals. This traceability was a small administrative feature with outsized operational consequences. Knowing an engine's recent operating profile allowed crews to anticipate likely failure modes and pre-stage parts before a problem occurred. It reduced days of trial and error diagnosis to hours of targeted replacement, and hours saved in repair translated into sorties available for the next wave. The laminar flow wing likewise demanded industrial exactness.
Laminar sections are unforgiving of surface irregularities. A single misaligned rivet or a subtle waviness in the skin can trip transitional flow into turbulence, erasing much of the theoretical drag benefit. That meant manufacturing tolerances and fit-up procedures mattered. The assembly lines were not merely welding metal. They were protecting aerodynamic performance through repetitive accuracy. Again, this is a point where production and combat meet. An airframe that left the plant with a properly faired wing would, hour after hour, burn less fuel at cruise and maintain higher speed where it mattered, at the altitudes where B-29s flew and interceptors contested the sky. That marriage of precision and throughput also had downstream effects on maintainability. A wing built to spec fits a replacement wing built to the same spec. A standard instrument panel allows a forward shop to swap a failed gyro with confidence that the replacement will mate without rework. These were not abstract efficiencies. They were decisions that shaped what ground crews could achieve on coral strips with limited shelter and improvised shops. The factory thus did two things at once. It made a better airplane, and it made an airplane that could be reliably repaired under combat conditions. Logistics, less glamorous than design but no less decisive, made those repairs possible. Fuel, ammunition, spare engines, propellers, hydraulic pumps, and even rivets themselves were items in a moving accounting problem that crossed oceanic space. Liberty ships and tankers carried bulk aviation gasoline in quantities that, by mid-war, had become the limiting dimension of American operations in the Pacific. Aircraft transport planes like the C-54 shuffled urgent spares forward when sea lanes could not afford time. Forward depots organized standard repair kits, complete sets of consumables and critical components, so a forward maintenance shack could execute a planned overhaul without waiting weeks for a single part. This is the machinery of sustainment. Predictable supply patterns that permitted riskier operations because planners could assume relatively fast replenishment. Concrete numbers help to anchor this argument. At Iwama, operational readiness of P-51 units regularly exceeded 80%, meaning 4 out of 5 Mustangs assigned to a unit were mission-capable on the books. That level of availability under forward conditions is what turned an experimental tactic into a doctrine. By contrast, multiple Japanese airfields reported serviceability that often dipped below 40%. The arithmetic is plain. If fewer than half your machines are flyable at any one time, the frequency and scale of your sorties are constrained far more tightly than those of an opponent who can put the majority of their fighters over the line. Those rates are not moral judgments about skill or courage. They are logistical realities that determine how often you can try to win a given piece of airspace. Operationally, the Mustang's engineering advantages translated into distinct tactical options. With robust high-altitude power from the supercharged Merlin, Mustangs could climb to and sustain the heights where B-29s operated, and they could do so with the fuel margins needed to cross hundreds of miles of empty ocean to rendezvous with bomber streams.
The laminar flow wing reduced drag enough to improve cruise fuel economy, let pilots arrive with more energy in hand, and buy extra minutes for emergency diversion. The bubble canopy reduced blind spots and improved situational awareness. The .50 cal Browning guns, plentiful and reliable, offered a consistent offense. When a Mustang pilot lined up on an enemy fighter or a flak position, he had a predictable burst pattern and ammunition margin to work with. When those elements combined in formation, the P-51's presence altered the calculus of defense around Japanese targets. All of which brings us back to April 7, 1945, not because that single day decides a war, but because it provides a concentrated view of how factory, logistics, and pilot craft produced an operational effect. Briefings the night before had been exact. Navigators reviewed waypoints out over blue water, plotted timing so rendezvous with B-29s would occur with fuel margins intact, and stressed emergency ditching plans.
Ground crews did the last checks that made each Mustang a predictable tool. Hydraulic lines examined, flap actuators measured for play, fuel pumps verified against leakage. Drop tanks were filled and secured. Batteries were cross-checked. Pilots did their pre-flight rituals. Straps and control feel measured with the same care manufacturing engineers had insisted upon months earlier. The takeoff was a testament to synchronized practice. Planes taxied and threaded into liftoff in tightly managed waves, prop wash and dust clouds momentarily blotting out the hangars. On long-range missions, formation discipline was not about parade ground aesthetics. It was fuel conservation and mutual defense. A few minutes off the deck, formations fell into cruising patrol. Engines settled into their efficient envelopes, and crews focused on navigation across the vast expanse that lay between island and target. For Japanese defenders, the sight of Mustangs over the capital was dislocating. Flight Surgeon Totani Mizu of the 56th Centi later described the moment as unexpectedly odd. Not so much because the enemy was there, but because the enemy behaved in ways that contradicted experience. Captain Yoshio Yoshida of the 47th Centi recorded similar surprise. Japanese planning had been tuned to prior engagement profiles, and the arrival of single-engine fighters with sustained presence at altitude forced rapid re-evaluation. Those accounts are not anecdotes of humiliation, but snapshots of a strategic surprise produced in factories thousands of miles away. When the two forces met over the approaches to Tokyo, the encounter compressed many of the war's tensions into a handful of minutes. The Mustangs, with their Merlins holding power at altitude, could often leverage energy tactics, trading altitude and speed to dictate the shape of engagements.
Japanese pilots flying Ki-84s and other late-war types still demonstrated individual skill and daring. In trained hands, these aircraft were capable and dangerous. But the Ki-84's operational reality was changing. Repaired with substituted materials, flown on lower-quality fuel blends, and maintained under chronically frayed conditions, the Ki-84s in many units simply could not sustain the theory of their design. Where on paper the Ki-84 could climb and accelerate at comparable rates, in the field, fuel adulteration, lack of spare parts, and limited overhaul facilities produced engines that lost compressive capacity sooner and were more prone to failure. The airplane's promise met the arithmetic of attrition, and attrition favored those systems that could replace parts fast. The engagements themselves were brutal and efficient. Brief, violent slashing passes, startled evasions, and the whirl of deflection shooting. These were the physical language of those dogfights. Pilots made the tactical choices that had been rehearsed. Conserve fuel when necessary, protect the bombers at all costs, engage only when the balance of risk favored you. Radio reports kept those choices tightly coordinated. Calls for support, warnings about fuel state, and terse announcements of hits and losses. A Mustang reporting low fuel after a skirmish was not an abstract phrase on a log sheet. It was a life-and-death indicator that determined whether a pilot might make an emergency touchdown on a friendly strip or attempt the riskier option of ditching at sea. Losses in such operations were real and often severe. Weather could convert a manageable mission into disaster. The so-called Black Friday operations had already demonstrated how quickly conditions could turn. Clouds rolling in from the ocean, navigational errors compounded by fatigue, and the unforgiving calculus of fuel margins all producing tragic outcomes. Operational statistics from the summer of 1945 underline this hazard. Roughly 85 pilots were lost in July-August 1945 during VLR and related operations. That figure is a sobering reminder that production and logistics, however robust, do not eliminate the human cost of sustained combat. Factories could replace machines in numbers. They could not replace trained men and women on a one-to-one basis with equal speed or ease. The human toll extended beyond pilot casualties to maintenance fatigue and attrition among ground personnel. Mechanics worked in rotating crews under tropical conditions, often in makeshift shelters with long supply lines behind them.
Maintenance cycles had to be compressed without sacrificing essential checks. This produced a pressure that occasionally led to mistakes, to cannibalization of serviceable airframes for critical parts, and to improvisations that were pragmatic but risky.
The factory-designed interchangeability mitigated some of those risks, but only when the supply chain remained intact and the flow of parts ran without long interruptions. When shipping losses, bomber interdiction, or port congestion delayed replacements, improvisation substituted for precision. And improvisation is a fragile pillar in the arithmetic of sustained operations. Strategically, the cumulative effect of repeated VLR missions and sustained escort operations was more than the sum of individual scraps. The psychological impact on Japanese planners and defenders must be weighed alongside the bare material facts. Observers in Tokyo recorded a shift in posture, more frantic scramble orders, altered defensive dispositions, and a pervasive sense that the locus of control had shifted. A bomber force that once feared operating without escort could now assume a higher level of protection on many missions. That change in assumption altered targeting doctrine, airfield survivability calculations, and the allocation of scarce Japanese fighter resources. Again, the key word here is capability multiplied by sustainment. A single P-51 over Tokyo might have been startling. Repeatable P-51 presence put stress on an opponent's decision calculus. But this was not a unilateral tale of success. The Japanese response to the Mustang threat contained ingenuity and tenacity. In some sectors, pilots adapted tactics, exploiting local terrain, cloud cover, and surprise when possible. Ground units experimented with dispersal and deception to reduce bomber losses. The human element, discipline, improvisation, and courage remained present on both sides. Importantly, many Japanese pilots continued to inflict losses and to fight effectively under conditions that would have demoralized less resolute forces. The narrative of industrial advantage should never be used to deny the skill or sacrifice of adversaries. Rather, it explains how those qualities were constrained by larger systems. Back on the production side, every loss generated managerial decisions. Depot chiefs and factory managers received reports indicating which parts were failing most often and what damage patterns combat produced. Those feedback loops allowed factories to adjust priorities. If a certain control rod was failing more often under combat conditions, production lines could be adapted to beef up its metallurgy or to increase the stock of spares. Engineers in the heartland read operational reports as data, not to gloat, but to refine. In this sense, the war effort was an industrially integrated learning system. The front fed the factory with lessons, and the factory responded with design tweaks, production shifts, or revised manuals that reached frontline crews in the next shipment. Those cycles of learning and adaptation mattered because the war's momentum was rarely static. Weather, enemy adaptation, and sheer attrition created shifting constraints.
A factory capable of producing a Mustang an hour could absorb a certain rate of loss and still sustain operations. Beyond that rate, the tempo faltered. Planners therefore paid continuous attention to the rate of consumption. How many engines were being exchanged each week? How many propellers needed replacement after raids that produced increased flak damage? And how many airframes required structural repair due to combat stress? These were the variables that determined whether operations like April 7 could be repeated without unacceptable degradation. As the campaign moved towards summer 1945, the cumulative pressure on Japanese industry compounded. Fuel shortages meant that even when airframes were available, the ability to fly them in numbers eroded. Lower octane blends and substitute fuels increased engine wear and reduced performance, turning what had been high-performing machines on paper into compromised tools in practice. Skilled technicians were lost to combat attrition or reassigned, and the substitution of less trained personnel into critical roles diminished quality control. Production capacity itself came under attack from strategic bombing campaigns that targeted factories and transport nodes. Each disruption created ripple effects through the maintenance and operational cycles. It is important to resist simple causal narratives. The Mustang's presence over Tokyo did not in itself cause capitulation. Rather, it was one element in a multifaceted pressure on a wartime system already strained by blockade, bombing, and resource scarcity. What the factory did do was change the geometry of options available to American planners. It allowed long-range escort to be attempted with reasonable odds. It produced a pool of aircraft that could be rotated into service with predictable readiness rates. And it supplied a logistical tail that made repeated operations feasible. Those systemic conditions contributed to a strategic environment in which air operations could be more daring, persistent, and costly to resist. When the smoke cleared on the flight decks and the maintenance bays, the qualitative contrast between systems became visible in more mundane ways. Where American depots maintained a rotating stock of spare Merlin blocks and standardized exchange kits, Japanese fields often logged lists of parts sought and parts absent. Where replacement engines could be sent forward by airmail priority or loaded onto a rush ship, Japanese repairers sometimes had to wait for inbound shipments that might be delayed by interdiction or port damage. These differential rhythms are the quiet mechanisms behind many battlefield outcomes. By the end of hostilities, the physical survivors told a story of distribution and endurance. Museums today display Mustangs that represent not only engineering achievements, but whole chains of production and repair.
In Japan, the lone K-84 at Chiron is a powerful artifact, a reminder of a machine that on paper promised much, but in practice was constrained by the grinding realities of wartime logistics. Both artifacts, preserved Mustang and preserved K-84, invite visitors to consider how design and supply interact, how courage meets metallurgy, and how strategic outcomes often hinge on the mundane arithmetic of parts and fuel. There is another legacy beyond hardware: institutional memory. The practices refined in wartime factories, modularization of components, standardized repair procedures, and integrated logistics planning, would inform post-war aviation and industrial management. Engineers and line workers who ran those lines carried procedural memories into peacetime industries, and the lessons of mass, quality, and sustainment shaped how nations thought about industrial power in the decades that followed. Finally, there is the moral dimension. The image of a Mustang silhouetted over Mount Fuji is powerful precisely because it compresses many things: engineering, industry, courage, and cost. Factories made the capability possible, and in doing so, they also made sustained combat and its consequences possible. That double edge must be acknowledged. Production sustained strategy. Strategy produced human cost. Histories that focus only on hardware risk flattening human experience. Histories that focus only on heroism risk ignoring the systems that made heroism possible. A measured account attends to both. If you stand now in front of a restored P-51, notice the paneling, the factory-made rivet rows, the serials stamped into the engine block. Those marks are not merely craftsmanship. They are traces of a system that reached across oceans to place American fighters over foreign capitals. The sound a Merlin makes it idle is, in a sense, the sound of industrial policy given mechanical voice. It is a reminder that wars are decided not only by daring do, but by the quieter, relentless output of shops and docks and trains. For those who want to see these machines and the places that made them, many museums preserve Mustangs and the stories of their manufacture. The Survivor at Chiron offers a complementary perspective, the other side of the same history. If you are curious to explore where to find these aircraft or to read the technical manuals and depot reports that shaped operational decisions, check the description for links and sources.
The factory that built the P-51 Mustang did not by itself win the Pacific, but it did something else that matters in the ledger of war. It converted design into presence, promise into repeatable capability, and potential into a pattern that could be sustained across months of operations. On April 7, 1945, that pattern showed itself over Tokyo, surprising pilots, altering calculations, and leaving a record of both engineering triumph and human cost.
The line that joined drawing board to strip was visible in the sky that day. An industrial shadow stretched into combat. And that shadow is the subject of this story. For more deep dives into the machines and places that shaped history, and for pointers on where to see surviving aircraft and archival records, subscribe and check the links in the description.